All right. Hello, everyone. My name is Peter Schulte. I'm the head of engineering at SarSatX, and my colleague Hosam Abduljalil is also here. We'll be sharing the presentation today. Hosam will start out with some explanation of SarSatX, a Saudi space startup company based here in Jeddah. And then I'll also share some details about our company, and then I'll give a technical presentation about spacecraft guidance, navigation, and control. So Hosam, would you like to introduce yourself and then get started? You're still muted, Hosam.
Yeah, sorry. Thank you, Peter. Good afternoon, everyone, and welcome. I'm Hosam Abduljalil. I have a background in software engineering and AI. I hold master degree computer science from King Abdulaziz University. I am currently the head of software and AI at SarSatX, and today I'm here on behalf of both SarSatX and the KU Aerospace Engineering Club to have this session titled Introduction to Guidance, Navigation, and Control in Aerospace Systems. Allow me to share my screen. Are you able to see my screen?
Yes, we see it.
Yeah. I will start with a brief introduction to SarSatX. Then I will hand over to Dr. Peter to talk us through the technical fundamentals of guidance, navigation, and control. We are a Saudi space tech company that provides satellite imagery, analytics, and AI. We serve multiple sectors like environment, energy, agriculture, and so on. We are a portfolio of wide accessibility ventures, KAUST, Lab 7, and Flat 6 Labs. Okay, the problems and the solutions. Before we begin, I would like to share two examples from more than 70 interviews we have conducted so far. The first one in front of you is the satellite image unveiled of an oil spill stretching 150 kilometers in the Red Sea, dumping nearly 1,000 liters, 100,000 liters of oil intentionally. So, and the satellite images is critical in detecting vessels that cause oil spills, which happen intentionally every day in the Red Sea and Arabian Gulf. So, to sustain and protect environmental assets, we can do this using the satellite imagery. The second example is with the farmers who can leverage this satellite imagery to check soil moisture, optimizing the irrigation routines, and let's not forget this viral for MENA region, where 75 to 95% of our valued water is dedicated to agriculture. So the satellite imagery helps to optimize irrigation and conserve water resources in MENA countries. You can see this image. This is full of clouds. You cannot give any useful information out of that because of the clouds and also the night. Yeah. So we adapted the advanced technology, the SAR, which is synthetic aperture radar, that can peek through clouds and see clearly even at night at a resolution as good as optical. Because SAR carries its flashlight, lightning things up. It sends out of radar waves, which bounces back from the Earth, giving us a clear picture, no matter the weather or time of the day. You can see these two images, the difference between the SAR and the typical or the optical satellite imagery over the Amazon rainforest. Regarding our products and services, we have a web platform called Earthlife that help our clients and users to go through the available analytics in different sectors and request defining their area of interest and request the service. Then after the result is ready, they will be notified and they can visualize the result on the web. Also, they can download the required results. The analytics services we provide in different sectors like maritime and environment, mining, and civil government, financial, and agriculture, and so on. Now I'll hand over to my colleague Peter Schulte to go through the technical details. Thank you all.
Thank you so much, Hosam. All right, you can go to the next slide. Yeah, so I'll just explain a little bit about our SarSatX team members. A few of our team members have actually joined us for the call today. Hosam, do you want?
Yes.
Yeah. Thanks. So we have, our team members have over 100 years of experience in the space and satellite imagery business. We have about 25 team members. One of our co-founders and CEO is Amr Alamoudi, and he's worked in Boeing and Northrop Grumman in the United States in the space industry. Then Dr. Ahmed Al-Zubairi is a graduate of the Aerospace Engineering PhD program at KAU. I'm sure some of you have met him before. Dr. Mohammed Al-Mutairi is an expert in synthetic aperture radar. He's our chief of business based in Riyadh. And Professor Matthew McCabe is a professor at KAUST, King Abdullah University of Science and Technology, and his research group is specializing in using satellite imagery. I'll tell you a little more about myself later. Darren Jordan, who's on the call with us, he has a PhD in synthetic aperture radar, and then you've already met Hosam. And our team's about 25 people. But this slide shows you a little bit of our strategy as a company. We're starting with the downstream, which is the applications, things like agriculture, oil and gas, planning cities, environment, watching for oil spills. And we're already doing business in the downstream. We purchase satellite imagery from other companies that have their own satellites in space. And then we do analysis on that imagery, like for some of the use cases that Hosam was explaining. And then what we're doing is we're learning what the market needs. All of our customers so far have been in Saudi Arabia. So we're really seeing what specific things do the Saudi customers want, which is different than what customers in other places around the world may want. And then we're using that information to help us decide what we want to build and launch into space ourselves. Let's go to the next slide. So what we started out with is developing an airborne synthetic aperture radar sensor. So we've done some tests using this sensor that we built using a grant from the Saudi government. And here's some of our team in the lab in front of the sensor. And in the middle, you can see an example of some of the images that we developed. This picture actually shows some electric power lines. And we can kind of get a different idea than just looking at a picture from a camera, because a radar sensor actually sends out radio waves that bounce back off of the target. And that gives us more information than just taking a picture with a camera. Let's go to the next slide. Here is our airborne radar sensor mounted in an airplane. We flew it on a test flight near Riyadh. And we just replaced the door of the airplane with plexiglass so that the radar could reflect through or bounce the radio waves off of the ground and back to the antenna through this door. And on the left side, this is the full image that we developed using the test flight. So it's got really great resolution and it gives us a lot of detail about the ground. And you can see this is the area where we were flying. There's a lot of fences and buildings that we can make out in this image. If we zoomed in and showed you a lot of details, this is really useful information that we're proving with this airborne sensor that we can develop this technology that then we will adapt to fly in space. And so I think the next slide talks about that. So yeah, right now our go-to market is we're working with major companies. So these companies on our screen are some of our customers and partners. We're selling satellite imagery and analytic solutions to these different organizations, or working with them to develop these types of solutions. And we're already making revenues off of this business using third-party images, even before we put anything in space. So our plan now is we're developing a constellation of 16 small satellites. We're calling it Saudi Eye. And these satellites 8 of them will be radar, synthetic aperture radar, which is our focus and our specialty. And the other 8 of them will be optical. And these satellites will fly together in a formation where there's a SAR and an optical together. So in the picture on the right side, you can see the blue satellites are SAR, and the red ones are optical cameras. So we put these 2 satellites near each other so they can get normal satellite imagery and also radar imagery at the same place at the same time on the Earth. And this will be one of the first commercial satellites for Earth observation launched in MENA, the first of this constellation. And we aim to get revisit rates, which means we pass over the Middle East region every hour. And this would really increase the ability to serve the customers that we have in the Middle East region. Right now, the satellite imagery that we get in the Middle East region is more like every 12 hours or every 2 or 3 days. And we also want to have every 4 hours revisit around the world. And we will own and operate these satellites here in Saudi Arabia. We'll have our own mission control center where we will operate the satellites and fly them. Let's go to the next slide. So our focus right now, like I mentioned, is on Saudi Arabia, which you can see kind of in the bottom left, a small square. But we hope to grow our market as we grow our company, as we start launching things into space. We'll begin working with customers around the GCC region, and then around the Middle East, North Africa region, and then globally. And there are other companies already using this technology, synthetic aperture radar. There are satellites from governments like the European Space Agency and Canadian Space Agency that have launched these types of satellites, but also private companies, Capella Space and Umbra in the United States, ICE-I in Europe, Synspective is a company in Japan. There's several other companies around the world that are already have their own satellites in space and are using this type of imagery to serve customers. So it's a well-established market, and we'll be entering into this market, but we'll have some unique features. Let's go to the next slide. So our primary focus is we're going to optimize our satellites for the Middle East region. The Middle East region, because it's near the equator, gets less frequent passes from satellites. In general, satellites go more often over the northern and southern areas of the globe, but not the middle regions. So we're going to specifically put our satellites in orbits that will pass over the Middle East more frequently so we can get better results for the customers that need to see things more often. Next slide. All right, so that's an overview of our company. Before I jump into the technical topic, though, I would love to just pause here and see if anyone has questions about SarSatX. So myself or Hosam or maybe some of the other SARSat team members that are on can help answer those. Go ahead, Ahmed.
Okay, hello, Peter and Hosam. Thank you for joining. Thank you for this opportunity. You just said that most satellites go to the northern or southern hemisphere. So isn't it possible to have a satellite around the equator?
Yes, you're right, Ahmed. So satellites around the equator are typically what we call geostationary satellites. So they stay over one point on the Earth. But these satellites are very far away from the Earth in order to stay over that one point. Basically, as the Earth rotates, the satellite rotates at the same speed.
Yes.
And that means that the images we would get from those satellites would not be a very high resolution because they're so far away. So we actually fly our satellites much closer to the Earth. They go faster. They go around the Earth multiple times every day instead of following that same point.
So in low Earth orbit, it's not possible to have around the equator orbit?
It is possible, but it's not easy to get a satellite into that orbit.
Okay.
Basically, it's more expensive because you have to spend more rocket fuel to get into a satellite with an exact orbit around the equator. So yes, it is possible, but it's not economical.
Okay, thank you very much, Peter.
Yeah, great question. Okay, feel free to think of other questions, and then at the end we'll have another time for question and answer.
Peter?
Yeah, go ahead.
Yeah, thank you. Would you mind share from your end and take full control?
I can do that, yes. You can stop sharing this one. Let me just get to the same slide. All right. Let me know when you can see the presentation. Okay, perfect. Alrighty, so what I'm going to be doing is giving you a background of guidance, navigation, and control. I'm going to focus specifically on attitude, determination, and control. I'll explain what all of those words mean because they're a little bit specific and technical. I'll tell you a little bit about myself. I'll explain attitude, determination, and control systems. I'll talk about some of the physics involved with them, and then some of the actual things that we put in space on satellites. And then I'll explain a little bit how we design a system for attitude, determination, and control. So my background, I'm from the United States, from the state of Texas. I studied at the University of Texas, which is the mascot of that university is the Longhorns, the cow mascot. And then I got a master's and PhD degree in aerospace engineering at Georgia Tech, Georgia Institute of Technology, in a different state called Georgia in the United States. But I really enjoy traveling. I've been living in Saudi Arabia for now over 3 years, and I've also visited many other countries around the world. And I love meeting people from different cultures and countries. I also enjoy music. I play the violin, both the normal violin and the electric violin. And then I love exchanging ideas about many topics with people who think differently than me, about philosophy and religion and many, many other topics. So if I ever get to meet some of you in person, I'd love to chat about anything that's on your mind. And then my own background before coming to SarSatX, I started out working on satellites as an undergraduate student, actually. When I was a freshman in my undergraduate studies, I helped to assemble a small satellite called Bevo-1. And Bevo is the name of the Longhorn mascot at the University of Texas. And we launched this satellite on the space shuttle before the space shuttle retired. And that was in 2009. And then I worked with several other satellite projects. Another one was called Fast Track. This was a test of GPS and using GPS on 2 different satellites to get a better estimate of the location. We also had a space mission design class as part of my bachelor's. So my team worked on designing a resupply vehicle to go to a theoretical space station between the Earth and the Sun. I also worked on a concept for a small satellite called a CubeSat with a solar sail. So it uses the sun's light actually to push it. And I did some analysis of what the trajectory of that type of system would be around the Earth's moon. Then when I was in graduate school, I got to work on a project called Prox-1, which was another small satellite. Also, ironically, it deployed a satellite that had a solar sail. So that was a neat experience. And then I worked with JPL, NASA's Jet Propulsion Laboratory, doing some of my research in my PhD related to Mars sample return, which is bringing rocks back from Mars to the Earth. And I also worked along with a company at KAUST called FalconViz on drones and used the same kind of technology I was developing for Mars to help detect problems on their drone. Then I've also had a really amazing opportunity to work at NASA, Johnson Space Center in Houston, Texas. As a summer intern, when I was an undergraduate student, I worked on the spacesuit program. So I actually got a chance to try on the spacesuit. This is a real picture of me in a spacesuit. This was before AI. The that I had this picture taken at NASA. And also I got to work on several different programs at NASA. One was the parachutes for the Orion spacecraft. So if you watch the Artemis 2 mission, you saw right at the end when they splashed down in the ocean that they came under these parachutes. I worked on designing the guidance and control system that were used with the parachutes. And we were doing test flights where we would drop a test spacecraft out of the back of an airplane in Arizona. And this is a picture from one of those test flights. I also worked on the space shuttle. Right after the end of the space shuttle, they were trying to understand a little bit more about the heat shield. That is when the space shuttle re-entered the atmosphere, it would get very hot on the bottom of, and sometimes the tiles would start to degrade. And so we were studying that. I also worked on the International Space Station program and helped develop a simulator that the crew used to train, the astronauts would use for training. But my main project most of the time that I was at NASA was on Orion. So actually the Artemis 2 mission was my primary focus for about 5 years, that I was working on guidance, navigation, and control software related to a lot of the things I'm going to discuss with you in this lecture. So that was a really neat experience to see what I worked on actually flying people going around the moon just a few weeks ago. And there's more exciting things coming from the Artemis program. So I'm excited, along with all of you, to watch the new developments. And it was also really neat to see a Saudi CubeSat being launched on the same rocket with Orion during the Artemis 2 mission, the Shams CubeSat from the Saudi Space Agency. Okay, so let's get into this attitude determination and control system. So the first thing I'll explain is this term guidance, navigation, and control. This is the name of the lecture, but what do these words actually mean? Navigation tells you where you are right now. So if you think about the GPS on your phone, one of the main things that it does is it figures out where on the Earth you're located by talking to satellites, actually. And we call this your current state. The state is just your location and your speed. Then guidance determines where you want to go. It gives you the desired state. So your GPS also does this. You put in your GPS on your phone, the location that you want to drive to, and then it tells you turn left, turn right. So guidance is that process of telling you which direction you need to go from where you are now. And then control is how you change from the current state to the desired state. So in your car, control would be turning the steering wheel, pushing the gas, pushing the brakes. That is how you change your car to move where you want it to go from where you are now. And there's two aspects of guidance, navigation, and control, especially for spacecraft, but this applies to airplanes as well. Translation, which is the location where you are, your position, your velocity, which is your speed, and your acceleration, which is how fast or slow you're changing your speed. And then rotational is also very, very important, especially for spacecraft. The attitude is the direction you're pointing. The angular velocity is how fast you are spinning. And then angular acceleration is how fast you change the speed at which you're spinning. So these two aspects, translational and rotational, are very essential for guidance, navigation, and control. We always need to know when we're flying an airplane or a spacecraft where we are and what direction we're pointing and how fast we're moving and how fast we're rotating. So all of those things are really essential for us. In a spacecraft, what's unique compared to airplanes is that spacecraft generally uncouple translation and rotation. So the orbit of your spacecraft usually doesn't influence the rotation of the spacecraft, and the rotation of the spacecraft usually doesn't influence the orbit. I say usually because there are certain situations where it makes a difference, but most of the time in space, you can treat them as completely separate problems. So we have one set of software and components that are focused on translation, and one separate set of software and components focused on rotation. So for this talk, I'm going to focus on the rotational part. If you have questions about the translation, we can talk about that later as well. But the rotation part is what we call attitude, determination, and control systems. So we already talked about attitude, that's the direction we're pointing. Determination is what is my attitude? And then control is how do I change from the current attitude to the desired attitude? Usually guidance gets lumped into control for attitude, determination, and control systems. And then the system actually is an important word because it tells us it's not just one thing. A system is multiple hardware, and software components that work together. And I'll break down what those things are later in this talk. So you can see here a picture of a space mission that was really essential for attitude determination. Gemini 8 was one of the early human space flights in 1966. It was the first time that two vehicles docked in space. And there was two astronauts flying this Gemini 8 spacecraft, and they came and docked with this Agena target. This was part of a rocket upper stage. But the astronauts, as they were flying the Gemini 8 capsule, they had to pay really close attention to their attitude, and they had to control their attitude by using their hand controller, their joystick. And actually this mission was very dangerous because after they were attached to the spacecraft, after they docked successfully, the Agena vehicle started spinning. And they didn't know why, and they started spinning so fast that they might have blacked out and even died. But the astronauts were able to separate from the rocket upper stage and slow down their rotation and safely return home. But it was really a dangerous situation. Even though they were successful in that first docking, that spinning was a really bad problem. And it was a result of a problem with one of the attitude control systems on the rocket. Okay, so let's talk about the math here, because math is a really important aspect in physics of how to do attitude determination control. First, we have several reference frames that we care about. The first reference frame is called Earth-centered inertial frame. And this is a reference frame where we just put the reference right at the middle of the Earth. And the x-axis comes out towards the vernal equinox. This is just a term for where the sun crosses the celestial equator. This is the celestial equator is the place that a place in the sky that the difference between north and south happens. So if you just draw a line out from Earth's equator, a plane, that's the celestial equator. And when the sun crosses that equator, that's where this vernal equinox happens. The z-axis of this frame comes out of the Earth's rotation axis, so roughly out of the North Pole. It's perpendicular to the equator, and then y forms a right-handed triad. So these are perpendicular axes. And we usually measure the spacecraft's attitude and position in this Earth-centered inertial frame. So here's a satellite. We have an X, Y, and Z position, and that tells us what direction we are with respect to this frame. So this frame doesn't spin. It doesn't rotate when the Earth turns. So the Earth is moving in this frame, but it is fixed to the center of the Earth. So it moves along with the Earth as the Earth goes around the sun. If we fly a spacecraft to another planet or another body like the Earth's moon, then we often use a different reference frame that's centered at that body. So we might use an Earth-centered frame around the Earth. We might use a moon-centered reference frame around the moon. We might use a sun-centered reference frame when we're going somewhere else. But we'll focus mostly on talking about satellites around the Earth today. And then another important reference frame is called the body fixed frame. And this is a frame that's fixed with the spacecraft and moves with the spacecraft. So the middle of it is at the center of mass of the spacecraft, and it rotates. So when the spacecraft spins, this frame also spins. And each spacecraft might have different directions here, but we always have to use a right-handed coordinate frame. And that just means that if you put your right hand like this in the camera view, hope you can see that, that shows you where the Z, the X, and the Y axes would be. A left-handed frame is the opposite of that, and we generally don't use that for spacecraft. So the attitude of a spacecraft tells you the difference between the body fixed frame and the Earth-centered inertial frame. So this is all that we're doing. We're saying, how has the spacecraft turned away from the Earth-centered inertial? So if they were lined up, that means that the x-axis of the spacecraft points exactly the same direction as the Earth's x-axis, and the same for Y and Z. But when the spacecraft rotates, then we're moving, and that's what we're keeping track of with attitude determination and control. Another reference frame that we use sometimes for spacecraft is called the local vertical and local horizontal frame. And this is a little bit different. It's centered at the spacecraft, just like the body fixed frame, but the direction of this frame is based on the orbit of the spacecraft. So we use, instead of X, Y, Z, R, S, and W. So the R axis is the direction of the position vector of the satellite. So the vector that goes from the middle of the Earth to the satellite center of mass, that tells us the direction of the R. The S axis is the direction of the velocity vector of the spacecraft. And then the W is a cross product. And something in the orbit is called the angular momentum vector. That's generally perpendicular to the plane of the orbit. And also you can use W cross R to get S, and you can do some vector math there to figure out these different directions. But we most commonly use this reference frame for relative motion between multiple spacecraft. So when I was talking about the rendezvous and docking, when that Gemini spacecraft came to connect with the rocket, they were using this local vertical, local horizontal frame to track their position with respect to each other. Okay, so let's talk a little bit about the physics aspects here. The first part that we have to think about is called kinematics, and this is a description of the motion. So you probably talked about kinematics in your physics class. For attitude, we use two different ways to describe attitude. One is called Euler angles, and I'll explain those. And then on the next slide, we'll talk about the second way. It's common for spacecraft called quaternion. So an Euler angle is what you probably have heard referred to as yaw, pitch, and roll. So for an airplane, Euler angles are very common. Yaw is how the direction of the airplane is turning. So it's rotating around that Z axis that's pointing down in this picture. The roll angle is how the spacecraft is rotating around the direction it's heading. And then the pitch vector is if it's pitching up, going up and down. And there's other sequences that we use for spacecraft called precession, nutation, and spin. I won't explain the details there, but this equation shows you how we convert from the Earth-centered frame to the body-fixed reference frame using rotations about these three axes. So you do a Z-axis rotation around an angle we call phi, an X-axis rotation around an angle we call theta, and a Z-axis rotation around an angle we call psi. So you can convert any position vector in the Earth-centered inertial frame into the body-fixed frame by rotating it around those three angles. So Euler angles are nice because they're really easy for humans to understand. Roll, pitch, and yaw are concepts that are easy for our brains to comprehend. But one of the challenges with Euler angles is they have mathematical problems that are called singularities. And the common term for singularities with spacecraft and aircraft is gimbal lock. So singularity happens when two of the rotation axes line up, and this makes you lose one of the degrees of freedom. So you can't actually describe your angle anymore. There's uncertainty. The same set of three Euler angles could translate to two different directions. And that can cause problems with computers and manual calculations of the attitude. So because of that, spacecraft generally use a different thing to describe motion. Instead of Euler angles, we use quaternions. It's a little bit harder for us to understand, but a quaternion is a four-dimensional vector. And it tells us two things. One of them is the direction that something is pointing, and the other one is the angle that it's spinning in that direction. So it takes those three Euler angles and puts them all into one angle around a single axis. And the math that we use to describe this is a little bit of complicated trigonometry. But you basically have a single rotation instead of three rotations. And that is much easier for computers to work with because you don't have the problem with singularities or gimbal lock. So you don't have that ambiguity. You can point in any direction without a problem. Okay, then the physics part of this is we take those descriptions in the direction that were rotated, and we can turn that into equations of motion. So using Newton's second law, you're all probably very familiar with this. The sum of the forces is the time derivative of linear momentum. So the mass and the velocity of your spacecraft, your aircraft, you take the derivative of those, and that gives you what's equal to the sum of the forces. And so we generally assume that mass is constant for satellites. Not exactly true because you have fuel tanks that may be using up fuel over time. But when we make that simplifying assumption, then we can just say that the force sum is mass times acceleration. And that's the rate of change of the velocity. For rotation and attitude, we do something similar to Newton's second law, but it's a rotational version we call Euler's equation. And in this, instead of the sum of the forces, we have the sum of the moments. A moment is a rotational force. And then instead of the time derivative of linear momentum, which is mass times velocity, we have the time derivative of angular momentum. And angular momentum is the inertia matrix times the angular velocity. The inertia matrix I'll explain more in a second, but it's like mass, but for rotating. And then the angular velocity is the speed at which you're rotating. And unfortunately, sometimes we can't use a constant inertia matrix. So that makes this a little more complicated. And we have to use cross products and some extra math to describe this. If it's constant, it becomes a little simpler, more like the mass times acceleration equation. So an inertia matrix, it tells us how mass is distributed in a rigid body. And most spacecraft we assume to be rigid bodies. There's exceptions to that. But for simplification, in talking about it as a concept, we kind of assume it's a rigid body. And what a rigid body means is that these numbers in the inertia matrix are constant. They're not changing. It's not changing shape as it rotates. If the rigid body has mass that's equally distributed, that means it's symmetric, then we have what we call a diagonal matrix. So this water bottle, for example, is mostly axisymmetric. It's in every direction, it's symmetric. It's not perfect in this direction, but in at least a couple of the directions, it's symmetric. I'm not sure, Mejo, if we're recording. I don't think so. One of the people who set up the meeting would have to start that. There is also, if the body is axisymmetric, then we have a simple matrix, just the diagonal on the X, Y, and Z axes. And that makes things a lot easier on the math. But if it's uneven distributed of mass, then these off diagonal terms in that matrix are non-zero. And that makes it a little bit complicated. So if the mass configuration is constant and not changing, like I said, if it's a rigid body, then we can assume this inertia matrix is constant. We usually do that for satellites. So rotation about different axes is stable, semi-stable, or unstable. So the major axis, which is the longest one, usually, the one that has the most inertia, is generally stable. And so that is rotation about the major axis would be around this long direction. So if you rotate like this, then you're stable from a physics perspective. Rotation about the intermediate axis is usually unstable. So in this water bottle, I think the intermediate axis would be like this. And then rotation about the minor axis is semi-stable. Those are specific physics terms you might remember from physics class. The water bottle actually doesn't have a minor axis because it's a circle on one side. Okay, so then if we have these equations of motion, we want to simplify them a little bit. So we make some assumptions, like I said, that the satellite's axisymmetric with even distribution and there's no external torques on the spacecraft. That's not always a good assumption, but for the beginning, we start out with that assumption. So we set the external moments to 0, to the left side of the equation 0. And then we can take this matrix and spread it out into 3 equations. So we have the X, Y, and Z, 1, 2, and 3. And the 3 terms of the inertia matrix and the 3 terms of the angular velocity. And then we have omega dot, which is the angular acceleration. So one important thing to note here is that the directions of rotation are coupled. So this is the X rotation equation, but it has Y and Z components in the inertia matrix and the angular velocity. Same thing in the Y and the Z. They have the Y has the X and Z, and the Z has the X and Y. So rotation and translation are a little bit different, and generally translation is independent. If you put in a thrust in X and Y direction, you're going to move X and Y direction and not move in Z. But if you rotate in one direction, you're also going to rotate in other directions, most likely. All right, so then how does this actually apply to satellites? How do we control satellites? The very first satellite that was launched by the United States into space was called Explorer 1 in 1958. There's a picture of these three guys who worked on it, holding it up, or holding up a model of it. And this spacecraft used something that we call spin stabilization. This just means that the spacecraft was always rotating, always spinning, and no matter what was going on, it was turning. And this is helpful because when a spacecraft's rotating, we can use the principle called conservation of angular momentum to keep us pointing in the same direction. So with the water bottle again, if I'm spinning this water bottle in this direction, it's harder for it to turn in a different direction. So it's generally going to stay pointed in the same direction if there's no other external torques or moments that are pushing it and trying to move it in other directions. So with a spin stabilized satellite, we only have to adjust occasionally. This saves power and fuel, but we have to have proper moments of inertia. This spacecraft, when they made the control system, they assumed that it was a rigid body, like I said, with that simplifying assumption. But if you see these wires here, these are antennas, and those antennas are flexible, and actually they dissipated the energy on this Explorer 1. So they actually caused some problems with the attitude control system. And spin stabilization was really common early on in the space exploration era. Some of the early spacecraft like this one used it, but it's not as common now because we have better control systems that we can use other techniques that are a little more effective. So the main technique that's used in modern spacecraft is called 3-axis stabilization. And this is where we hold a fixed attitude without rotating. So we're pointing, for example, at the Earth, at the sun, at the moon, at something else that we want to look at, or we want our spacecraft to be oriented in a certain direction. So we can point cameras, we can point science instruments, we can point solar panels toward the sun, but we have to constantly adjust our attitude because in space there's things that cause you to rotate. So even though I said we assume that there's no external rotation torques, actually in reality there are. And I'll explain some of those. Gravity gradient torque, I'll talk about on an upcoming slide. Solar radiation pressure means the sun actually pushes you. This is how solar sails fly that I mentioned earlier, but it also can cause your spacecraft to rotate because it doesn't push evenly on both sides. You can have magnetic torques if you have a magnetic field on your spacecraft, and the atmosphere can push on your spacecraft. Even though it's thin in space, in low Earth orbit, at some altitudes, it's enough to cause your spacecraft to rotate over time. And then a third method that's also rarely used in modern spacecraft, but it can be sometimes, is called gravity gradient torque, or gravity gradient. And we use this to align the long axis with the vector that points toward the gravitational pull. So often it looks like the kind of standard configuration would be what we call a barbell with two big masses on the end of a long stick. And when you put a spacecraft shaped like this, it will stay pointed towards the Earth as it goes around the Earth. So you can see that A is pointing towards Earth and B is pointing away. As it orbits, it'll keep rotating to always point toward Earth. And this is useful for some types of space missions, but it's not very, very common on modern spacecraft. Okay, so now let's switch to talking about hardware and software. How do we actually measure our attitude? How do we know what direction we're pointing? And we do this with instruments that we call sensors. Sensors are pieces of hardware that tell us what direction we're pointing and what direction we're spinning. So first is an inertial measurement unit, or IMU. And this is really just a computer chip. And this computer chip is measuring the rotation rate. So it has two things inside of it, a rotation measurement device called a rate gyroscope, and then a translation measurement device called an accelerometer. Your phone actually has an IMU inside of it. That's how it knows what direction your screen's pointing. It's how it measures things when you're looking at a 3D picture or something like that. It uses an IMU inside of it to do that. One of the nice things about IMU is that it's purely kinematics. You're just measuring the rotation rate and the translation rate. So you don't have to know anything about the forces or the dynamics or anything like that. And the computer on board this computer chip integrates those equations of motion that I showed earlier, both the rotational ones and the translational ones. So an IMU has to know what inertial frame it's measuring with respect to. Usually that's the Earth-centered inertial frame. And there's a couple different types of gyroscopes that we use in IMUs. One of them is called a strap-down gyroscope. And that's where we rigidly attach this chip to the spacecraft and it rotates along with it. And then the other one is called a ring laser gyro. This is also common. It's very small. It's like on a computer chip, but it actually uses the theory of relativity, so Einstein's theory, to measure the distance that's traveled by lasers as the spacecraft is rotating and those lasers are moving. So really interesting tools that we use. These are really tiny devices usually, but they're really important. And then another type of sensors we use for our attitude is called visual attitude sensors. And these are sensors that we mount at a known location on the spacecraft. And we know exactly where it is and what direction it's pointing in the body frame. And then we can measure the direction to some body in space. So there's three types of bodies we look at. A sun sensor, which is this top. We measure just the angle to the sun. Really, it's just a solar panel. And it just measures how bright or dark the sun is on that solar panel. And that tells us what direction the sun is pointing with respect to the body frame. So if we're pointing toward the sun, it'll be very high measurement. If we're pointing away from the sun, it'll be very low measurement. And in between, there's a range where we can see different angles that we're pointing. This is usually a rough attitude measurement. So this is used like in the beginning of a mission when you first come off the rocket to initially find out what direction you're pointing. An Earth horizon sensor is not super common these days, but it used to be more common. And we can use this to measure the direction to the Earth's limb or horizon. So this is where you can see space above and Earth below. And then a star tracker is very common. It's more for precise attitude control. And a star tracker is just a camera that looks at the stars. And it literally uses a catalog of stars to say what direction you're pointing. So you can measure your direction to one star or to multiple stars. And a lot of satellites use this for very precise direction knowledge. And it has an onboard computer catalog that keeps track of where stars are, and it looks at the picture of the stars that it generates, and then it just tries to match where you're pointing, what direction you're pointing. Because the stars are generally fixed with respect to the inertial frame of the Earth. They move at a very, very slow rate, so we can assume that they're inertial for the purpose of spacecraft attitude determination. Another sensor we use sometimes is called a magnetometer. And this is basically a spacecraft or a sensor that measures the Earth's magnetic field. And so similar to a visual sensor, we mount it on a fixed location on the spacecraft, and we use it to measure the direction of Earth's magnetic field. So Earth's magnetic field is in kind of a known location and direction. As we rotate around while we're flying around the Earth, if we know where we are, we know what direction Earth's magnetic field should be pointing. And when we rotate, the magnetometer measures that it's pointing in a certain direction, and we can figure out where we are with respect to the inertial frame. All right, now that was sensors. That's how we determine our attitude. That's our navigation. Now let's talk about control. How do we change our attitude? A very common method of attitude control for large spacecraft is called reaction control system thrusters. So this is what the Apollo lunar lander used. This is a picture from the lunar lander. You can see it's basically small rocket engines that fire in the directions of the principal axes of the spacecraft. The Orion spacecraft also uses these. And we fire some small amount of rocket fuel to induce torque that makes our spacecraft rotate. And so we have to use fuel, and it requires mass. We need fuel tanks on board. So this is only used for either large spacecraft or small spacecraft that have to do a lot of very high performance maneuvers. And to avoid complex motion, we generally, like I said, line up those thrusters with the directions of the principal axes of the spacecraft. And we can originally we would rotate around each axis independently. So around X, around Y, around Z. But there's modern control techniques that computers can actually fire multiple thrusters and rotate in multiple directions at the same time. If you watched the Artemis 2 mission, you saw the astronaut Victor Glover was doing this when he was flying around the upper stage of the SLS rocket during the proximity operations demo. He was manually rotating using a hand controller that was firing these thrusters to make him rotate. And this is a low performance device, and it's not very, very precise, but if you need to move quickly, it's really helpful for that. But you can't do a lot of precision with it. Another very common form of attitude control is what we call the momentum exchange devices. There's different kinds of these, but this is basically a spinning wheel that we use to create rotation or to keep us from rotating. So the wheel rotates and there's an equal and opposite reaction. Remember Newton's second law? That when we rotate in one direction, our spacecraft rotates in the other direction. And we put usually 3 wheels on the principal axes, the X, Y, Z axes, or we might include 4 wheels if we want redundancy in case one of them breaks. So momentum wheels are kind of an older type of attitude control system where they're always spinning, and then we go faster or slower to change the direction that we're pointing. So that's a neat tool. Reaction wheels are very common in small spacecraft that are not very precise. So these are wheels that are not spinning until we want to rotate, until we want to point in a different direction. So we command the wheels to go in different speeds in a certain direction and speed. And we do this when we're reacting to a disturbance torque. So let's say the atmosphere of the sun is pushing our spacecraft and we want to push it back the other way. Or if we want to intentionally point towards a specific direction, point towards something on Earth, point towards the moon, point towards the sun, we command these reaction wheels to spin. Another more precise and more advanced attitude control system is called a control moment gyroscope. So this uses change of direction to create a torque. So there's a flywheel on a gimbal. So it's a spinning wheel that also can spin around in different directions. The reaction wheels are in fixed directions. And so the gimbal axis, the thing that rotates that is fixed in the body frame, but the spin axis can be turned by a motor, and then the speed of the spin can be changed by a different motor. So these are a little more complicated devices, but they give us more precise control of our direction, which is really important for certain things, like you want to look at an exact specific point on the Earth, or you want to be very precise in pointing a certain direction so you can dock with another spacecraft. That's something you would use a control moment gyroscope for. So let's watch this quick video. I might have to share my screen again for the sound to come through. So let's try it, and if the sound doesn't come through, let me know and I'll pause and reshare. Okay. Sorry, thanks for letting me know there's no sound. Let me try resharing it. Second. Start the video over. Apologies for that. This is an important video because it explains why rotating wheels inside a spacecraft can actually move the direction. So the sound should work here. Just give me a thumbs up if it's working.
When I hold the spinning wheel, nothing crazy happens. But when I flip it, I spin. Flip it back, and I stop. Flip it, I spin. So the question is, why am I spinning? So I have to force the wheel to turn over. Now Newton's third law says that for every force, there's an equal and opposite force acting as well. So when I force the wheel is applying force equal and opposite onto me, causing me to turn. So the same thing applies when I'm on the ground, but the friction between my shoes and the ground stop me from spinning. So another way to explain what's going on is through conservation of angular momentum. Now, angular momentum is something that tells you how hard it is to either start or stop something from spinning. And it depends on two things. One, how fast it's spinning. We call that the angular frequency. Two, its shape, or what we call the moment of inertia. So this wheel is rotating counterclockwise. Now I'm going to teach you a trick. So get your right hand, and I want you to curl your fingers in the counterclockwise direction. And you see that your thumb is pointing upwards. We'll call that the positive direction. So see, this wheel has positive angular momentum with a magnitude of L. Angular momentum is conserved. That means that as long as there are no outside forces, the total angular momentum of the system always stays the same. So when you flip this thing over and do the right hand trick, your thumb points down or in the negative direction. So the angular momentum of this wheel is now negative L. So the whole system, me, the turntable, and the wheel starts out at negative L. But when you flip the wheel now has positive L. So the whole system needs to stay at negative L because of conservation of angular momentum. So I need to spin with angular momentum of negative 2L. That's why I spin the other way.
All right, so that's just illustrating kind of with a simple demonstration why turning a wheel inside a spacecraft makes it spin. Because just like when he was on the turntable, there was no friction, nothing holding him back from rotating. When you're standing on the ground and holding that spinning wheel, the Earth is actually stopping you from spinning. But in space, when you're floating, your spacecraft's just floating free, and it doesn't have anything to resist it from spinning. Okay, one more actuator is called a magnetic torquer or torque rod. And this is really just a coil of wire wound around a metal core. It can look something like this. This can be something that you make in a lab. Some universities, they build these themselves. And you run an electric current through that wire, and it actually generates a magnetic field. And because the Earth has a magnetic field, that will cause your spacecraft to spin when you turn the torque rods on and off in different directions. So these are rough attitude control, but they're often used, for example, to stop a spacecraft from tumbling or spinning when it comes off of a rocket. This slows down that spin so that you can gain control of the spacecraft. Okay, so some example spacecraft and their attitude control system, Orion, which just flew in Artemis 2, has reaction control system thrusters. So on the service module here, you see these little thrusters pointing out, and they are used for controlling the attitude of Orion. And then actually after the crew module separates and is ready to re-enter the Earth's atmosphere, there's also reaction control system thrusters on the crew module. You can see little cutouts here for those thrusters. But during most of the flight, they use the service module thrusters. And then the International Space Station is really, really huge spacecraft. It's about the size of a football field, in a football stadium. And it uses control moment gyroscopes, but they're really huge control moment gyroscopes, like larger than a person. And it uses those to rotate. Okay, so how do we actually take this and design a system that we use to control the attitude of a spacecraft? First of all, we have to have requirements for our mission. And those mission requirements will, what we call flow down to the requirements on the attitude system. So, for example, the mission requirement may say, I need to point my camera at Saudi Arabia every time I fly over it. And that gives me an attitude requirement that flows down saying my spacecraft has to be capable of pointing towards Saudi Arabia when I'm flying near it. Or you might have another requirement for your power system that says, I need to have 100 watts of power for this portion of the mission. So you might need to point your solar panels towards the sun for a certain percentage of the mission in order to have that amount of power for that time period. So that's what we mean by flowing down requirements. So each of the pieces of the spacecraft has a role to play in maintaining those high-level goals of the mission. So pointing a payload like a camera or a science instrument would be one reason why we have to have an attitude requirement. Another that I just mentioned is power generation. So our solar rays have to point towards the sun enough that we get enough power to not let our batteries die. We also have a thermal requirement. So if you point toward the sun, things get hot. If you point away from the sun, things get cold. You may have things on your spacecraft that you need to warm up or that you need to cool down. So that can tell you directions you need to point. Communication is also important. If you want to talk to the Earth, a lot of antennas only work if you point them towards the satellite dish on the ground that you want to talk to. Or if you have laser communication, you have to point that laser very precisely towards the terminal that's receiving the other end. Another thing is reorienting for stability for maneuvers. So let's say a maneuver is generally when you want to change the orbit that you're in. That means you fire a big rocket, not to change what direction you're pointing, but to change where your orbit is by increasing or decreasing your velocity. So you've got to point in the right direction and you have to hold the big rocket in that direction for long enough to complete that burn. Some burns are very long, especially with electric propulsion systems. They can last for many minutes. Some burns last just a few seconds, but even for that, you need to be pointing very precisely and stable so that you keep pointing that direction to get the right orbit that you want. Another issue that attitude systems have to handle is called jitter. And jitter just means how fast you are moving when you are trying to hold a specific attitude. So if you have jitter on your camera, so let's say you were taking a picture with your phone, if your hand's moving, that phone picture might be blurry. Spacecraft have the same problem. If the spacecraft's jittering, then the images that it takes might not be precise enough. Okay, so the next step after you've defined the requirements for your attitude system is to select your components. You have to choose sensors to do the navigation, knowing what direction you're pointing. You have to choose actuators to control the attitude out of all the options that I already talked about. And you also have to write algorithms or choose algorithms, existing algorithms to control all of those things. So the inputs from those sensors have to go through algorithms to give you your navigation state to tell you what direction you're pointing. And you need another algorithm to determine what direction you want to be pointing, a guidance algorithm, attitude guidance. And then you need a control algorithm to tell you when to fire your thrusters or when to turn on your reaction wheels or your control moment gyroscopes. And all of the things that influence a spacecraft design also influence which of these you might choose. So some of them may be requirements of how precisely you need to know what direction you're pointing. If it needs to be very, very precise, you probably need a star tracker. But if you can have it looser, then maybe a sun sensor is good enough. Or you might have need to very precisely control, or you could have looser control requirements. So the tighter or looser your requirements are, the more advanced of a sensor or an actuator you need. Also, mass and volume and power are really important considerations on a spacecraft. If something's too heavy, then it's going to not fit on your satellite, or it's not going to be affordable to launch it. If it takes up too much space, then it might not fit on a small area that you need on a rocket. Or if it takes too much power, you might not be able to get big enough solar panels to generate enough power to operate that. And then cost and schedule are really important selection criteria too. If something's really expensive, you can't afford it. If it takes a long time, it may cause your launch to end up later. So you have to consider all these things when you select your attitude system. There's two primary approaches that we use for CubeSats, which are small satellites. And these are typically individual sensors or actuators that we purchase. So we can buy sun sensors or star trackers or magnetometers. We can buy control moment gyroscopes. We can buy reaction wheels. We can purchase them individually and create our own attitude determination control system, or we can purchase an integrated system where it just takes up part of your CubeSat. So let's say you had a 3-unit CubeSat. It's 10-centimeter cubes. Maybe one of those units is taken up by an attitude system that has thrusters built in or sensors already built into it. Both of these methods require you to do integration, software and hardware integration. That means you connect the hardware to other pieces of hardware on the spacecraft, and also the software has to talk to other pieces of software. So you have to define interfaces between all those pieces. An interface is just where two pieces come together. And you also have to make sure that they're compatible. So let's say your power system has to provide the right voltage for your sensors and for your actuators. And then you have to write the algorithms, actually write out the software, the algorithms for navigation, the algorithms for guidance, the algorithms for control, the sequencing of the mission. Sometimes you have different algorithms at different points of your mission. And also fault protection. This is looking for problems and fixing the problems if you find them. So all of these are different pieces of the system you have to come up with. And then once you've chosen all those pieces, you put them together. And this is what the integrated system looks like. You start with an attitude determination. Well, let's say you start with sensors. And the sensors just look at the spacecraft, how it's rotating, and measure that. Then that feeds into the attitude determination algorithms. It's a software that tells you what direction you're pointing based on what the sensors are telling you. And then the output of the attitude determination algorithms goes into the attitude control algorithms. It says, I'm pointing this direction, and then I want to point this direction, and then you rotate. And to rotate, you send a command to your actuators. Your actuators start something spinning or fire a thruster, and then that influences your dynamics of your spacecraft. And then you start the loop again. So this is constantly happening all the time in any spacecraft, this loop. Okay, that is the content that I had. I just wanted to show you a little bit of some sources here. This material came from a course that I helped to teach at Georgia Tech for undergraduates on flight dynamics, and also a course that I took as a student in my undergraduate at the University of Texas. And here's some other websites that have really useful information about CubeSats and about attitude determination systems that you can look into if you want to learn more about this topic. And then lastly, here's my contact information if you want to get in touch with me by email or on LinkedIn. We are looking for interns and new employees that we're hiring at SarSatX to work on our project. So you're welcome to take my contact details if you're interested to get in touch, or even just to talk about any of these things or ask questions. I'd be happy to interact with any of you. So I think we can now go to questions. So we can take questions either about the attitude determination and control presentation or about SarSatX, really any other topics that you all are interested in. And Hosam and some of the other team members may help me depending on the questions. But yeah, I'm open anytime. Go ahead.
Thank you. Thank you both for your insightful presentation, Peter and Hosam. You can find a Google form in the chat for the attendance and sharing your series.
Great. So yeah, if anyone's interested in sending your CV to us, you can use that form and organizers will pass it on. So yeah, any questions? Ahmed, go ahead.
Okay, thank you for the session, Peter. I always have a question in my mind when I see actuators on the Orion or Space Shuttle or anything. The gas thrusters, for example, when they move in one side, how is it stable and, for example, moves 5 degrees per second, then stops? So I know that maybe there is another reaction the other side, but I'm not sure how is it so stable like I saw in the Orion mission.
Yeah, that's a great question. So you're right. What they do is they fire the thruster in one direction, like this, to start moving. And then to stop moving, they fire the thruster in the other direction. So, but it's very stable because they do a few things. First of all, they optimize those control algorithms to be as precise as they can. And they do a lot of simulations and testing. And so through all of that, what we call control system design, they are able to make it be as stable as possible based on the moment of inertia of the system and based on the capability of the thrusters. I hope that answered your question.
Okay, great.
Feel free to just unmute your mic and speak if you have a question. Yes, go ahead, Osama.
Hello, everyone. I have a question about the axis. In the four-dimension axis, there are two parallel. If they are aligned, what type of cracks will be of the spacecraft? If they are aligned on the same problem with the software or the hardware?
Sorry, Osama, I couldn't hear your voice very clearly. I think you're asking about the axes of the spacecraft, but I couldn't hear exactly what the question was. Could you repeat it?
About the axis, yes. You say that if they're aligned, the angle, if they're aligned, there will be a cracks or the software can't read it clearly. So what's the problem will be on the life?
Yeah, that's a great question. So let me give you an example. If you think about latitude and longitude on the Earth, when you are at a point on the Earth, your latitude tells you the angle above the equator that you are, right? And then your longitude tells you your rotation around the poles. But so your latitude is 0 degrees when you're at the equator, and it's 90 degrees when you're at the North Pole. Your longitude is the rotation around the Earth, right? So it's, 0, 10, 20, 30 degrees, all the way around to plus and minus 90 degrees. But when you're standing on the North Pole, your latitude is 90 degrees, but your longitude, you don't know. Because you can point in any direction and you don't know what your longitude is. I hope that makes sense. So that's an example of this idea that we call a singularity. And the problem that happens is actually a mathematical problem where when, let's say, you rotate, like with an airplane, sorry, I'll pretend this water bottle is an airplane, right? If you rotate straight up and down, if your airplane's flying directly up, then you could have a problem where your pitch axis is pointing in the roll direction. And then you don't know when you turn, is it a pitch or a roll? So that's kind of the problem that happens. The mathematical problem is related to trigonometry, and in some angles, you can't have, like when your sine or cosine is equal to 0, then you have some problems. That's the mathematical reason. But this is the reason why we use quaternions. Even though they're harder for us to understand and conceptualize, they don't have those mathematical problems.
Thank you.
Yeah, that's a great question. It's a complex topic. Go ahead, Ahmed.
Yes, hello, doctor. First off, I wanted to thank you for taking the time to explain this to us. And my question was, for us as aerospace engineers, since our coursework is mostly focused on aerodynamics and propulsion, aircraft design, what opportunities or assignments would aerospace engineers have in SARSAT or in satellite applications?
Yeah, great question, Ahmed. As I studied aerospace engineering, I also did things related to aerodynamics and aircraft as well as spacecraft. But there's a few things that I would recommend. As a student, you can participate in some challenges or student projects. So I know that the Saudi Space Agency has several of these types of projects where you can design a satellite or you can take some courses related to space if they're not offered in your university. SarSatX has an internship program, so that's one of the reasons why we asked you if you're interested to submit your CV at the link that was shared in the chat window. And there's opportunities to learn and utilize those skills. We also do a lot in our company with computer programming. So even if you haven't worked with spacecraft before, if you have experience with AI or some of those types of programming things, those are skills that we're also looking for that are important for what we do with satellite imagery. And one other opportunity I'll mention is NASA has a global hackathon they call NASA Space Apps Challenge. And I know that there's been some, they do it virtually sometimes and they do in-person things sometimes. And I think there's been some events here in Saudi for that.
Yes, thank you, sir. And a follow-up question.
Sure.
For your internship program, are you looking for more of graduate students or people already graduated, or could students also apply? For example, third year, fourth year?
Yes, third year and fourth year undergraduates definitely could apply for that internship.
All right, thank you, sir.
Yeah, no problem. I see we also have some of our other SARSAT team members on the call. Would any of you have any questions you want to ask?
Thanks, Peter. That was a great presentation. I do have one question related to determining your absolute pointing direction. From the presentation, it sounded like star trackers are the best for that use case. I wanted to know, for terrestrial applications, dual GNSS has become quite prominent for angle determination. I wondered, is that being used in space as well, or is star tracking just the way to go?
It can be used in space. I think volume-wise, it might be a little bit restrictive, but there's nothing to say that you can't do that. No, it's probably usually on larger spacecraft than we're looking at for our company, but definitely possible.
Great, thank you.
It may be more of a research area though, and not as much of a commercial product at this point. Great. Any other last questions about SarSatX or about anything we talked about today? I see a question from Abdullah in the chat. He asks if the internship is only for Saudi students or also residents. Either. We can have either Saudi citizens or Iqama holders welcome to apply, even if you're not a Saudi citizen. Hosam, go ahead.
The aerospace student in the past. Can you give us advice about the future during our period of study? What kind of advice you can give us?
I think you're asking for advice about your future career path. Is that right, Osama?
Yes, I'm sorry. My mic is not very good.
That's okay. Yeah, so my suggestion is applying for internships is a really great way. Even if you don't get accepted to the StarSat internship, obviously we couldn't have all of you on this call join us as interns. We only have a small team and a limited number of slots for internships, but having an internship in any field is a really useful way, from my perspective, to learn about what you enjoy and learn about possible career paths. So for me, doing internships was very helpful for even understanding why I was studying certain things. The other thing, even if you can't do internships, is practical projects are very, very helpful. So whether that's building a drone or a model airplane or satellite, or even coding projects, hackathons, things like that, those types of practical applications really help you to learn things that you wouldn't learn in your classes. And I really highly recommend them. Or even external courses or extracurricular activities like this Aerospace Engineering Club are great ways to expand both your knowledge, but also your network and other skills like communication skills and organization skills that are also very important in your career, even sometimes more than your technical knowledge. Great question, Hosam. Okay, if there's no more questions, I think we can end the session. Thank you all so much for your attention. Great questions. And also, I hope sometime that I can come and meet you all in person at the university. Our office is actually quite close to King Abdulaziz University. So we'd love to have you come visit us sometime, or to come in and see you at another meeting of your organization. Hope you all have a great day. Abdulaziz, any other announcements or things you want to say before we close? Okay, thanks everyone. Have a great evening.
Thanks, Peter.